Okay, so let's get started. So any questions? So we will, today we will talk about counting, and maybe after an hour or so, we will pick up on the sample midterms and discuss some of the problems in the sample midterm. And if you have any other questions, I'll answer them before, going into the sample midterm. So any other questions about the logistics? I noticed that finally all but 3 of you have taken the practice test. So and hopefully, yeah, again, if you're experiencing any problems with the test setup, you should let us know so that we can try to fix it. Any questions? So are you ready for the exam? Can you take it now?
I do have a question. I was wondering if the exam was going to be more like the practice midterms or like our homeworks.
Well, I guess it's a little bit of both. So I cannot. So if maybe you can clarify exactly what your question is, because I don't know exactly. You're not going to upload the answer. The exam will be mostly like a typical test on Blackboard, right? So the questions will be presented to you, and you'll be either typing in your answer or filling in, if there are multiple choice questions, then you will answer them by clicking boxes and things like that. Or if there are free response questions, then you will simply type in your answers into the text box. So Courtney, you asked me, will it be like this or like that? And I'm not entirely sure what the difference is. Yeah, maybe she's frozen. Okay, good. So any other questions?
Will we be able to ask questions during the exam? Like maybe there's like some notation we don't understand, or we need a question clarified. Is there any way we can contact you?
No, you can definitely contact us. So if you have a question, then the best way to contact us is, use your phone to, either call us, or I think it's better to just use the phone to, post something on Piazza. Just keep it ready to go, right? And if you must, post a question, then announce that that's what you're going to do, right? That way, when we look at the video, we will know, it'll not look suspicious that you are, fiddling around with your phone, right? When you take the exam, your phone should be far away from you. So you need to get up to access your phone. And when you do that, just let us know that, this is what you're doing. And then, take your phone, enter your question on Piazza, and wait for the answer. And then you can see that from the way this whole process works, it's somewhat painful. So we hope that, the questions are clear enough, and you don't have to ask questions. But if that's, if there is a need, then this is, I think, what can be done. If somebody else has a, better suggestion, let me know. But this is, the environment is not, it's not the most natural one for taking exams. Greg?
For the short responses, for the short response answers, is there a scenario where we might need to use like the for all or the there exists symbols?
Right. So when that's there. I will post an article on Piazza telling you what to do for math symbols. Okay, there
Okay.
shouldn't be too many, right? And obviously for all the propositional symbols, you can just use the English word like and, or, not, and so on, right? And for all and exists, you can just say for all exists, right?
All right. Thank
So,
you.
so just, as long as we should be able to figure out, from the context that you are referring to the symbol and not, not using it as a word in English. So that's, largely what we are going to do. And I don't think there will be a need to, go beyond, these symbols. Okay. Any other questions?
Are we allowed to use sheets of paper during the test?
Right. You are allowed to use sheets of paper. You can have like, 3 or 4 sheets of white paper with you. During the environment video, just show it to us so that we know it's, blank, right?
Oh.
But other than that, feel free to use scratch paper to, work out your answers. But all the answers are going to be entered on Blackboard. So it's not, you would not be submitting those sheets of paper. It's just scratch paper for you.
Okay. The scratch paper can be line paper, right?
Yeah,
Okay.
just blank. That's all. Any other questions?
I don't know if you can answer this. This is just like a general question. Do people generally run out of time or have time issues on the test, or is it more like you have enough time, you know how to solve it, or you like can't think of a solution?
So this is a little bit hard for me to say. If it is possible that some people will run out of time. Okay. It is also possible that people might finish in half the time. It's a little bit hard for me to say, right? I mean, whatever it is, it's obviously been far too long since I was, in your position. So it's a little bit hard for me to judge exactly how long it's going to take. But the questions are, neither hard nor easy. Okay.
Thank you.
I don't think they are tricky. So at least for the first exam, I prefer not to make it tricky because that's sometimes very frustrating. But what else can I say? So there will be some questions where multiple answers need to be selected, right? So and it goes without saying that if you have multiple choices that are applicable, obviously there has to be negative points, right? Because otherwise everybody will select all choices, and then of course that includes all the right choices, right? So I will post an article that explains exactly how the negative points work for those questions. But the bottom line, the one thing you should know is that no question will earn less than 0, right? So if you completely mess up a question, it's not that you're going to end up with a -3 points for the question, right? So it's just 0. But questions other than these select all applicable choices, those types of questions will have negative points, but not other type of questions won't have negative points. Anything else?
Will we be allowed to backtrack 2 questions? Or
Yes.
Okay.
You will see questions one at a time, and you can go back when you want. So again, one high-level strategy that I want to tell you is that it's not necessary to get every question right, but make sure that the questions that you are really focusing on, try to get them really right, because at the end of the day, if you get 5 questions out of 10 right, okay, and you really get them right, then I know that you have, enough of the material to move on, right? But if you just get a little bit of each question right, then that doesn't quite tell me anything. And it is also probably not a good idea for you to split your time that way across questions, because each question is logically it's a parts, a number of parts that are related to each other. So if you spend the time on one question, you might as well get all of its parts right. And I think that's a good strategy for you. And it's also a good strategy for me to figure out who is having trouble and who's not, who's on top of the material, right? It's understood that you're going to make mistakes. And I've mentioned before, I'll mention it again. So typically the averages in these exams are, could be anywhere between 50 and 70, right? So if it is higher than that, great. But just because you get a 60 in the exam doesn't mean that you're doing badly, okay? Anytime we design a test where we want to test how well you understand the concepts, it's not possible to design the test in such a way that the average will be 90, okay? The average will be 90 only if I show you the same problems 100 times and I ask you to solve it for the 101st time, then a lot of you will get a 90 plus. Otherwise, it's not that you won't do well, it's just unpredictable, right? And as a result of unpredictability, the average might not be good. So what I want to say is that, don't be discouraged or anything just because the average is lower. Which is also the reason why, you should try to do well in every question that you pick. And if you do well in half the questions, then you are probably going to be fairly close to the average already, just because you assuming that you score nearly the full score in all the questions that you focused on. Okay. Any other questions?
For the multiple choice questions, would we have to explain our thought process?
So there are different types of questions. So there will be some questions where you don't have to explain, and there are other questions there where you will have to explain.
Is there going to be partial credit?
Again, depending upon the, if it's a free response, obviously there's partial credit. If there is a straight up, multiple choice question, right, then there is no room for partial credit there, right? Any other questions? Okay, very good. Let's get started.
If we
Yeah?
do work on scratch paper, do we have to upload that or
No,
no?
no. There aren't. So what we want to see is that if you work on scratch paper, then there will be something that you will write at the end, and that's all we want, right? So if it's a proof, use your scratch paper to work through the proof, but then enter the proof, properly on the on Blackboard. Okay, so that's the scanning during the exam is quite difficult, because once this webcam is going on, you can't really do too much. So it's not the easiest thing. So we will just stick to entering everything on Blackboard. Any other questions?
Do we have to show?
Yeah, go on.
Do we have to show what we're writing to the webcam?
No, all I want to do is I want to be able to, so when you write, if you sit a little bit back from the laptop, again, not all of this is feasible because you have a working surface and it has so much width, and you have to live within those constraints. But what we would ideally like to do is, when you are working on your piece of paper, we would like to be able to see that that's what you're doing, right? So although we may not be able to see the paper itself, if we can see that, okay, what you're doing is writing and not, say, talking to somebody else or looking over or things like that, then that's again, this would really help us to get through the proctoring quickly and not really have to talk to everyone to say, what were you doing here, what were you doing there, because ideally, the exam will be done. We will look through the videos and everything will be good, and there is no need to sort of revisit the test, right? So that's what we are hoping for, and as long as you keep in mind that you are trying to clearly show where you are, then I think everything should be fine. Again, don't stress too much, okay? So you're not going to get everything right in the exam. You're not going to get everything right about how to take a test in front of lockdown browser, but everything will get resolved, and yeah. So there is nothing that we cannot work out. Any other questions?
Yeah, so this test would be one of 3 tests, right?
Correct. So there will be another midterm. The date for that, at least tentatively, has been set already, so you can find it on the course webpage, and then there will be a final. Okay. And okay, so let's get started. And the next topic is counting, right? So we were talking about summations in the last lecture. So today we will talk about counting, and let's start with an example, right? So world's best donut shop is everybody wants to buy a donut there.
You're not sharing your screen.
Oh, what happened? Why is that? Okay, yeah, good. Thank you for telling me. Let me go back to, I think it just died on me. Yeah, I think it went to sleep and then stopped broadcasting. Okay, so everybody wants to buy a donut at this shop because they want to service the maximum number of customers. The shop sells just one donut per customer, and the chef insists that every donut be distinct. So now, if there are 10 possible flavors and 8 possible fillings and 5 possible toppings and 8 possible sprinkles on top, right? So again, this is the flavors. Okay. Okay, somehow it just crashed. Okay, so if there are 10 possible flavorings, 8 possible fillings that go inside the donut, and 5 possible toppings, and then sprinkles that go on top of the toppings, how many different donuts can we build, right? So this is, of course, a simple problem that most of you already know how to do. It's the basic product rule that says that you simply multiply the choices. And so if we say that the flavors is represented by the set F, the filling is represented by the set I, the topping is represented by the set T, and then the sprinkles is represented by the set S, then you have the composition of the donut can be captured as a sequence of these 4 choices, okay? And then we can use, you know, what you know from high school about counting problems like this, or we can use our what we learned about cardinalities of sets that we learned earlier in the course. So if you have n finite sets, right? And then you want to know the number of elements that can be formed using a sequence of elements drawn from each of these sets, right? So a sequence of elements from each of these sets is nothing but an element from the cross product of all these sets. So what is the size of that set? It's given by the product of the sizes of the individual sets, right? So this is something that we looked at when we were learning about the cardinalities of sets. So that tells us very simply that you know, the number of possible donuts is, you know, 10 flavors, 8 fillings, 5 toppings, and 8 sprinkles. And so by picking a different value for each of them, you can get 3,200 distinct donuts. And this approach of taking the individual choices and multiplying them together is called the product rule, okay? And the key assumption in the product rule is the choices are independent of each other, right? So for instance, if somebody tells you that if you have this topping for the donut, then you cannot have any sprinkles, right? So once those kinds of dependencies are there, then you cannot simply use the product, right? But if the choices are independent, if you're told, you know, no matter what the flavor is, you can have any filling, and no matter what the filling is, you can have any topping, right? So if you have no constraints and all the choices, all the 4 choices here are independent, then you can simply multiply them, and that gives you the total number of possibilities. Okay? Any questions on this? Okay. So then, you know, after the product rule, there is a sum rule, right? So if there are 60 students in CSE 150 and 50 students enrolled in CSE 350, how many students are enrolled in the 2 courses together? Anybody wants to tell me?
110.
And why is it okay to add these 2 numbers?
It just wants a total count.
Right. So Kaylee?
I was just going to add that there's no overlap.
Right. So the assumption is that 150 is, I think, a prerequisite for 350, and therefore chances are, or let's say we know that there is no overlap between the students in the 2 classes, and therefore it's okay to add. So the sum rule basically says if you're taking the union of sets, if the sets are disjoint, right, then union essentially translates into the plus operation on the size, right? Just as the set product operation translates into you know, integer product operation on the sizes, the same way the sum rule says that the union operation simply translates into plus on the sizes, provided the sets are disjoint, okay? And again, always keep in mind that there is a similar requirement here, which is that the choices be independent. Okay, so for instance, if you talk about CSE 150 and AMS 210, there are certainly some students who take these courses together, and therefore you cannot simply add up the number of students in each course because you need to, then you'll be double counting students that are taking both courses, right? So most of the time you need to, it's not that you have just a single rule that you can use, either product or sum. Typically you need to combine the two rules, okay? So I'll give you an example, right? So variable names in Fortran 77, which incidentally is the language in which I started programming first, right? So so in Fortran, the variable names can be 1 to 6 characters long, okay? So you can't have arbitrary length names, just 1 to 6 characters. And then they must start with an uppercase letter, and all the subsequent letters can be either letters or digits, okay? And in addition, Fortran 77 only allows uppercase letters, right? So the lowercase letters you can think of as if, they don't exist. So the first letter can be any of these 26 uppercase characters, and the second and subsequent characters can be any one of these 36 characters, right? Or any of the uppercase letters or the 10 digits. So how many possible names are there? Does anybody want to take a guess or tell me what the number is, the number of possible names? It's going to be an expression, so obviously you can't calculate it, but so what I'm looking for is an expression. If you want to type it on the chat, you can do that. When I'm specifically looking at it, it is easy for me to see. Or you can, raise your hand and then speak. Greg?
Something along the lines of F times S plus 2FS plus 3FS plus 4FS plus 5FS.
Okay, so I think the expressions are, okay, so Sam says 26. Okay, so let's see. So the answer, one of the answers I see is 26 times 36 to the power 5, which is close. If you consider all 6 character letters alone, then this is the number, right? So the first character can be chosen in 26 ways, and the subsequent 5 characters can each be chosen in 36 ways. So if you have, one letter from F, another from S, another from S, another from S, another from S, and another from S, then this sequence, based on the product rule, is going to have this many possibilities, right? So that many identifiers are possible if you stick to characters of names of length 6, but what we want is names of 1 through 6, okay? So that's the next answer I see. So let's go through exactly how to do this. So we can have, so basically what we need to do is we need to say, okay, what if the name has just one character, then it's just F, right? Just one character. That's, if you have 2, then it'll be a sequence like F comma S, right? Because the first character is from F, the second character is from S. If you have 3 characters, then you have F comma S comma S and F comma S comma S, comma S, and so on. Okay. So the size in this case is going to be just F. In this case, it's going to be F times S. In this case, it's going to be F times S square, F times, right? So if there are 3 letters, right? So then or 4 letters, then the first letter can be chosen in F ways, and the remaining 3 letters can each be chosen in S ways. So you take the product of all of them, you get F times S cube, right? So let's see that here. So 1 character is F, 2 characters is F times S, and then F times S square, and so on. So you add up all of these, then you get an expression like this, right? So again, this is just like we have a summation notation, we can apply that to any operation, right? So what this says is it simply expands to, you know, you set I equal to 0, so you get F, I equal to 1, then you get F cross S, then you set I equal to 2, then you get F cross S square, F cross S cube. And so on, okay? And then, so since, you know, obviously these are all disjoint sets, right? There is no 1-letter word that's going to be the same as a 2-letter word. So all these are disjoint unions. So they can be turned into summations, and the choices in each of these, like if the first letter choice is completely independent of the second letter choice and completely independent of third letter choice, and so on. Therefore, the Cartesian product operation can be turned into multiplication in integers. So essentially this expression will become something like this, right? Because we have just replaced the product here by integer product and the union here by summation, right? So this is what we have simply applied the product and summation rules, and we get this expression, and then we get this sequence, which this is basically a geometric progression that we already saw in the last couple of lectures, how to sum it up. So we have a closed form expression for the summation that's like this, and then you add it up, you get this number, which is 1.6 billion, right? So that's the number of possible names that you can define. So hopefully there is not a program that requires more than, you know, this many different names, right? So so again, often we come across problems where we have to use multiple rules, right? And yeah, so many of you, multiple of you have the right answer. So that's good.
Excuse me.
Yeah.
Does it have to be 6 characters, or it could be any certain length from 1 to 6, right?
It is 1 to 6 characters.
Okay, that's why. I got it.
Right? Yeah, that's why you have to do this complicated union. If it was always 6, then the answer is, you know, just 26 times 36 to the power 5, right? So if it's always has to be 6 characters. So now, often there are additional constraints in our choices, and we need to factor those additional constraints when we count. So let's say that we have M awards that we want to hand out to N persons, right? So we can represent the award as a sequence P1 through PM. Okay, what that means is P1 is the person that was given the award A1. P2 is the person that was given the award A2, and up to PM is the person that was given the award, that was given the Mth award, right? So it's just a way of representing who got the award, right? So we can, what you will see here is that for counting, we are trying to represent everything as a problem on sequences because we are quite used to counting sequences. And so we want to, try to represent any counting problem as a problem on sequences, okay? So that's why when you say M awards are being given, we want to kind of represent that as a sequence, okay? And this is one way of representing that sequence. And so now we can say, hey, if there are no constraints on who can get the award, right? Then, the award A1 can be given to any of the N persons, right? And the award A2 can be given to any of the N persons and so on. So we can say that P1 can be chosen in N ways. P2 can be again chosen in N ways because it can be any of the persons and so on up to PM, right? So therefore, the total number of possibilities is what? Somebody can just answer the question because it's simple enough that we don't have to go through a long process. Or it's too simple that nobody thinks it's worth answering. Okay, so how many possible such sequences are there when you have each of P1 through PM? You can choose in N ways.
N to the M.
So the number of possibilities, I guess it's already there, which is why nobody's answering. I usually have the answer in the next slide, but well, okay, so now I understand. Okay, so the number of possibilities n to the power m because you have n times n times n times. You do that. You do the multiplication of m times, and you get n to the power m. So, but what happens if each person can win only one award, right? So then now the answer for that is not here. So people can try to answer that question. Anybody wants to try? You can lift your hand and answer. Okay, so we just add a condition that once you give the award A1 to someone, right, that person can no longer get any other awards. So how would we go about counting the number of possibilities when that additional condition is added?
First would be -1.
Okay, so let's see. So when we pick who is going to get the first award, right? So how many possibilities are there for P1? Anybody? Yeah, go ahead.
N possibilities for P1.
Right. So P1 in this case can have n possibilities, right? So there is no constraint on who will get the first award. But what about P2? How many people are left for getting, in terms of choosing P2, how many choices do you have?
n-1.
Right, so you have n-1 because the person who won the first award is no longer in contention for the second award, right? So therefore, you eliminate the person who's already been given an award, so you have only n-1 choices for the next one, right? So what about P3? How many choices are there?
n-2.
Right, so it's n-2. So you can see the pattern. So for PM, there is going to be n minus m plus 1, right? So the m minus 1 persons that already got an award are no longer eligible for the mth award. So the number of people that the mth award can go to is n minus m plus 1, right? So now these choices are all independent. So at this point, we can apply the product rule. So this kind of product rule, which takes these kinds of additional conditions, is called a generalized product rule. And the generalized product rule basically says that if there are ni possible entries for the ith position, then you just take the product, right? So there are n1 possible entries in the first position, n2 possible entries in the second position, and so on. Then the total number of entries is obtained by simply multiplying the possibilities for each position, right? And which in this case is, I guess I switched from m to k. So, but, you know, so then you have n into n minus 1 times n minus 2 all the way to n minus k plus 1, which can be more compactly represented as n factorial divided by n minus k factorial, right? Any questions? Okay, so let's look at another problem. Let's call a dollar bill defective if dollar bills have 8-digit serial numbers on them, okay? And we will call them defective if the same digit appears more than once in that serial number, okay? Of course, it's not defective really, because you know you will find that most, a lot of dollar bills do have repeated numbers, but just for the sake of this problem, we'll call it a defective dollar bill, okay? So the question is, how common are defective dollar bills? So how would we go about solving a problem like this?
You could try to calculate first how many effective or how many valid dollar bills there are.
Okay, so let's calculate, but even before, let's calculate how many possible dollar bills are there, right? So what's that number? Anybody else wants to try? Again, there is 8-digit serial number, each of which consists of digits. Greg?
Just 10 to the 8th.
Right, so, right, eight digits. Each digit can be any of the, 10 possible numbers. And so 10 possible digits. So the total number of possibilities is 10 to the power 8, right? So now number of non-defective so what is this number? How can we calculate the number of non-defective ones?
10 factorial divided by 2.
So we can apply the same calculation, right? Because it's the same problem, right? So once we use the first digit, we can choose in any of the 10 ways, but the second digit is constrained because whatever we used for the first digit cannot be reused for the second digit, and then whatever we used for the first 2 digits cannot be used for the third digit, and so on. So you end up with the same formula as here, which has this form, Okay. So the fraction of non-defective bills is, we just divide one by the other, right? So it's 10 factorial divided by 10 to the power 8 times 2, right? What do you think this number is? Anybody wants to take a guess on what this number could be? Again, obviously you're guessing, right? So it's not, if it's off by a factor of 5, that's okay. Is it, do you think it's 0.5, 0.2, 0.01? What do you think it is? That's a very good number. So, so the number is, 1.81%, right? So, which means that if you look at $50 bills, 49 of them will be defective, right? So, so a lot of dollar bills are actually defective. Anyway, so that just shows you how to, solve these kinds of counting problems. Now let's take a slightly different, problem. Pieces on a chessboard. Okay, so you have 3 pieces: a pawn, a knight, and a rook. Right? You don't need to know what these pieces look like or what they do in chess, because that's not, what we are trying to do here. The only thing you need to know about chessboard here is that it's a 8 by 8, grid, right? So that's all you need to know. Okay, so it's an 8 by 8 square grid. So we want to count the number of different ways in which these pieces can be arranged on the chessboard so that no 2 pieces are in the same row or in the same column. Okay, so we can represent one of these positions by a sequence of these 6 values. So RP is the row of the pawn, CP is the row of the column of the pawn, RK is the column row of the knight, column of the knight, row of the rook, and the column of the rook, right? So those are the 6 quantities. So how can we go about calculating the total number of possibilities if you have this condition that no 2 rows or columns are the same? What would be that number? Owen?
Well, for the pawn, there are 8 possibilities for the row and for the column. And then for the knight, there are 7 possibilities for each of them. And for the rook, there are 6 for each of them.
Right. So it's basically the same kind of problem. We can solve using the same technique. And then if you do the calculation, it turns out that there is, 113,000 possibilities. Okay. So, so that brings us to sort of the problem of permutations, which is, again, something that you have come across in high school, or, maybe not in high school, maybe in middle school. But so the permutation of a set is a sequence that contains every element of S exactly once, right? So a single permutation is simply one sequence, right? So you take the elements of the set and you write them down in some order, and that is called a permutation. Okay. the questions generally refer to how many permutations are possible, right? How many permutations are there that are distinct from each other. And we can count that in the same way that we have been doing so far. The first element of the sequence can be any of the n elements. But once you have removed that element from the set and put it in the first place, for the second position, you have to choose one of the remaining n minus 1 elements. Then for the third position, you have to choose one of the n minus 2 elements, and so on. And therefore, the formula we arrive at is n factorial, right? The difference between what we have been doing so far and what we are doing now is that we are constructing a sequence that consists of all the elements, right? So whereas here, we were, the number of, for instance, if you, so in this problem, there are 10 possible digits, but we needed only 8 digits, right? So that's why you have this 10 factorial by 2. But if you have 10 digits and you're talking about 10 numbers with 10 digits, then you will simply get a 10 factorial as the number, right? So, so permutation basically, you have this formula that if you have n elements, then in a set, then the number of possible permutations of those n elements is simply n factorial. Okay. So far we've talked about the product rule and the sum rule. So now we will talk about the division rule, right? So let's look at another chess problem to sort of understand what the need for this kind of a division approach, right? So now you're again asked a problem about arrangement on a chessboard. And once again, you're given the same constraint that the pieces have to be on distinct rows and columns. The only difference is that the pieces themselves are not distinct, right? They're identical, 2 identical rooks. Okay, if the rooks are distinct, then we already have done the problem and we have the answer. But if the rooks are the same, then what's going to happen is that we are going to say, here is one position and here is the other position. The only difference between these 2 positions is that the 2 rooks, their position has been switched, right? So for instance, I have, okay, it's going to be difficult for me to draw an 8 by 8. So you could have, one rook sitting here and the other rook, sitting there. And over here, we might, this might be R1 and this might be R2. And out here, all we may do is we may do R2 here and R1 there, right? But since the 2 rooks are identical, we cannot tell the difference between these 2 positions, right? And so what we would do is we would basically say, hey, we'll count it as if everything is distinguishable, but then finally divide up by the number of positions that are basically identical, right? So that is the division rule. So what it says is that if you have a mapping from A to B, that's a k to 1 onto function, okay? So which means that everything in B is covered, and k to 1 means k elements of A are being mapped into one element of B, right? So then you can say that because each element of B is being mapped from k elements of A, you can say that A equals k times B. Notice that we are all talking about finite sets in all these counting problems, right? Because otherwise, the question itself doesn't make any sense, right? So how can I ask you how many if it's not finite? So because we are working with finite sets, we can, say things like this, that if there are, k points that map to 1 point on B, then the number of points in B should be 1 by k times the number of points in A, right? And so that's what we are doing. We are saying that, hey, here is a set of possible configurations, right? So in this case, A is possible configurations of distinct rooks, and B is possible configuration of identical rooks. And what we are saying is that many configurations that are distinguishable when the rooks themselves can be distinguished, they all map into the same case here when the rooks are identical, right? And since there are two rooks, and so we can say that the k in this case is going to be just 2, right? Because either we have one rook here and one rook here, and then we flip them, then that produces a second position, right? So you're not going to confuse these two. These two can be confused, but you're not going to confuse anything else. So the k here is going to be 2. So the division rule basically says, applying the division rule, you can say that if the roots are identical, then the number of possible positions is obtained by just dividing the original number by 2, because 2 such positions should be counted as just 1, right? Any questions on this? So that's the third rule that we added, right? So product, sum, and now the division rule. Okay, so let's try to generalize this a little bit further and make the problem, more interesting, right? Let's say you have n knights that are seated around a circular table, okay? And the question is, how many distinct ways are there to seat them, okay? So what do you mean by distinct? We are going to say that 2 seatings are considered the same if, the 2 seatings match exactly in terms of who is sitting next to who, right? So each knight is, if you think of a circular table, then each knight is going to be sitting in between 2 other knights. And we would say that if every knight is seeing the same pair of people on their either side, then we would consider that as the same seating, okay? So now, how do we figure out how many such seatings are possible? Okay, so let's again start with a simple problem where, we don't worry about, this notion, and we simply calculate the total number of possible seatings. And then we have the seating, we can, so let's say that the circular table has m seats, right? Then we can capture the seating position by a sequence k1 through km. So this is the knight that's sitting in the first position in the table. This is the knight sitting in the second position in the table. And this is the knight that's sitting in the last position in the table. And then we already know this formula because the first position can be any of the knights. So we have n possible ways to fill the first position. We have n-1 ways to fill the second position, and so on until we have n-1, n-m plus 1 possible choices of knights to fill the last position. Okay, so if the seats are completely distinguishable, then we have this many possible seatings, right? So this is our from our generalized product rule. Okay. Now what we need to do is we need to apply the division rule to recognize seatings that are indistinguishable, right? So can you tell me how many indistinguishable seatings are there? Okay, so we can.
Oh, is it n minus 1 factorial over n minus m factorial?
No, it's n factorial, right? Because there are n knights. So the first position can be filled in by any of the n knights.
No, I was thinking after the division rule. If you divide by n.
Okay, so let's go step by step.
Okay.
You're almost there, but it's not exactly that. So so let's think about, right? So we have one way to do that. Let's try to take instead of looking at m, let's look at 3, right, or 4, right? So we have, so let's say this is a table, right? So let's say A, B, C, D, right? And now we can do D, A, B, C, right? And C, D, A, B, and then B, C, D, A, right? And you can see that as far as who is sitting next to who, all these 4 seatings are identical, right? So there is no difference. And so you can kind of imagine that, okay, so when you rotate the seating by any number of positions, right, it doesn't change who is sitting next to each, right? So if you have m seats, then by simply moving everybody to the right by 1 without changing the knights who are sitting there, right, you will get something that's different according to this count, but but it's really indistinguishable. So what we need to do is we apply the division rule, but we okay, so right, because there are m seats, so you can do m rotations around the table, and each of those rotations will result in exactly the same number of right. So that's exactly what is on the chat. Yeah. So in the n minus 1 factorial is sort of what one might immediately say, and then thinking about it a little bit more, you realize that what you need to divide by is m rather than n, because m is the number of seats around the table. Okay, so you end up with a formula like this. Any questions? So far we have seen the product sum and generalized product and the division rules. And again, I don't think any of these are things that you don't know at all. You probably have seen all of these either done problems somewhat like this, either sort of informally as a puzzle or something like that. So we haven't done anything totally new so far. So and we are going to continue to not do anything that's totally new. And the next thing that's not totally new is how do you count subsets? Okay, so how many 5-card hands can be dealt from a 52-card deck, right? Or how can I select 3 toppings from 10 available toppings, right? So what you're asking for in each case is a subset of 5 elements from a 52-element set, a subset of 3 elements from a 10-element set, right? So this is what you're asking for. And so how can we do this, right? Can we apply our product and division rules to get the answer, right? So we can again take, let's take this example, right? So the first topping can be chosen. The first topping can be chosen in 10 ways. The second one can be chosen in 9 ways. The third one can be chosen in 8 ways, right? So that gives you the number of possible sequences. But these are sequences and we want sets, right? And we know that if there are, this is a sequence of length 3, right? So we know that from a set of length 3, we will produce a sequence of 3 factorial number of different sequences, right? So if you want to count the set rather than the sequence, then we should simply divide this by that number, right? So again, we are counting the sequences that represent the toppings, and we know how to do that using our generalized product rule, and we apply that. And then we say, hey, we are not really interested in the sequence, we are interested in a set. And then we use the division rule, which simply tells us how to, to essentially divide by the number of distinct sequences that we can get from a set of the same size. So the general rule is this, right? So this is, if you are looking at, if you're interested in the number of sequences, then that we already have the formula n factorial by n minus m factorial. Now, this tells us how we can pick a sequence of length m. So we have to divide by m factorial if you are only interested in the set, right? Because we don't care in what order these toppings are chosen, because the only thing that matters is what toppings are there on your pizza, right? The order in which they were put on your pizza doesn't change how the pizza tastes. And same way when we talk about a poker hand, it's a combination of cards there that counts. It doesn't matter exactly in what order the cards were dealt, right? So we need to divide by this number, and so we get this expression. And because this subset counting is something that happens so often, we have a notation for that, which says, which is pronounced as, n choose m, right? So we say that among n items from an n item set, choose an m item subset, and n choose m captures how many distinct subsets of size m can be chosen starting from a set of size n, okay? Sometimes this is called the number of combinations as opposed to the permutation problem that we looked at, okay? So now let's go back to our donut shop, right? So we saw that the donut shop was not able to sell, that many donuts in a day. Let's go back to how many we were able to sell. Well, 3,200, donuts is, may seem like a good number, but, businesses want to sell, more, right? So, so let's say, so to increase the sales, the management says, let's not sell them 1 donut per person. Let's sell them, a dozen donuts, okay? But the chef is picky and says, well, I want to make sure that everybody gets a unique experience, so every box has to be different, right? I cannot sell the exact same dozen to any 2 persons, right? So remember, we had, I think 3160, I think was the number, right? Right, 3160, I believe was the number. So if there are 3160 possible donuts, and we are going to put 12 of them, 12 of them in a box, how many distinct boxes can we make? Or rather, how many donuts can we sell in a day? Can you tell me what the formula is? Someone can lift their hand. 3,200? Okay, 3,200. Okay. I think that's right. So what's the number of donuts they can sell in a day? Again, let's state, Greg.
3,200 factorial divided by 3,200 minus 12 factorial. And I think it should be choose, so divided by divided by 12 factorial as well. Or
Right? Okay. What do you think this number is? We don't have to, do this. We could just have said, 12 times 3,200, choose 12, right? Okay, so how large do you think this number is? A million, a billion? How big is it? So this 12 is just simply that each box has 12 donuts. So I'm multiplying that by 12. Greg?
Since we're dealing with such large numbers, roughly 3,200 to the 12th power.
Right.
Or or 3,200 to the to the 12th power,
right.
I think.
So the number is 28 decillion, right? So, or if you write it in scientific notation, it's 2.8 times 10 to the power 34, right? So clearly the management has hit a home run, right? So now they can sell lots and lots of donuts. So before we finish, I'm going to show you something a little bit more interesting that that I don't think many of you would have seen before, right? So we're going to start by introducing a problem that seems decidedly uninteresting, right? So how many n-bit sequences have exactly k ones, right? So let's say I take 8-bit sequences. Let's me take an example of 8 and k is 3, right? So an example is 0, 0, 1, 0, 0, 0, 1. Yeah, so that's, I guess it's not the right example. So let me fix that. Okay. Right, so that's a sequence of zeros and ones with exactly 3 ones, right? So you can see that once I pick what the 1 positions are, I'm done, right? So to count the number of n-bit sequences with exactly k ones, all I need to do is to decide how many possible ways are there to choose these 1 positions, right? So this is again a subset problem because I'm simply choosing the subset of positions where there is a 1, right? So this is going to be simply the n choose k problem, right? So pretty lame as an example to discuss, right? But let's go back to another variant of the donut problem, right? So the management can now sell lots and lots of donuts, but producing those 3,200 types of donuts still takes a lot of time, and packaging different donuts into your box is also a lot of work. So the management wants to streamline the production by saying, let's just have 10 types of donuts, okay? And the chef says, well, again, I want to make sure that everybody gets a unique box. So the question now is, with these conditions where there are only 10 distinct donut types, okay, how many boxes can be sold? So the point is that obviously, you can sell a box that's all one type of donut, or you can sell a box with 2 types of donuts or 3 types of donuts, all the way up to 10 types of donuts, right? So you can apply your sum and product rules to consider these 10 possible cases separately, and within each case you will have you'll have to worry about, okay, if I have, let's say, 3 types of donuts, then how many types of the first donut do I have, how many types of second donut do I have, and also which donut types do I pick for the 3 types that's going to go into this box, right? So this, when we think about it this way, it's quite a complicated problem, okay? But there is a different way to think about it, which makes the problem so almost trivial to solve. And so what we do is we are going to arrange the donuts, right? Let's say the first. So we are going to map this into a binary string problem that we just went through, okay? It's a binary string problem with exactly k ones, right? And the way we are going to do this is simple, right? So we are going to have a sequence of zeros and ones, right? And we are going to let the zeros represent the donuts and ones represent the border between 2 types of donuts, right? So let's say donut type 1, so we're going to say donut type 1, right? And then donut type 2, donut type 3, 4, 5. Okay, so this is one arrangement, right? So there are 12 donuts, and you have all 10 types. Okay, so we could represent this as, the donuts are going to be represented as zeros, And the boundary between two types of donuts is going to be represented by a 1. So you're going to put a 1 here, 1 here, 1 here, 1 here. Oh, no, not that one. Okay. 1 there, 1 there, 1 there. Right? So this binary string represents one possible way of filling the donut box, right? And you can see that any such binary string with 11 ones, right, is going to define one unique way of filling the box. Not 11, 9, right? I have only 9 ones. Okay, because there are only 10 possible donut types, which means I will have only 9 boundaries, right? So I need 9 ones. So, and then I need 12 donuts, right? 12 zeros and 9 ones, right? So any binary string with 12 zeros and 9 ones is going to represent one unique donut box, right? So then, can you tell me what is the number of such donut boxes? So how long is the string? The string is 12 zeros and 9 ones. So there are 21 positions. And then you have to decide which of the 9 positions among this 21 contains a 1, right? So that's going to be 20, now 1, choose 9. Okay, so that's the number of ways in which you can, create distinct donut boxes, right? And one way to, if I gave you this problem in the homework without telling you this trick, and then if you worked on it for 2 days without making enough progress, then you'll see how impressive this trick is, right? So there are so let me stop here, right? And what we will do is we'll take a 10-minute break, and then come back, and I will answer questions relating to your relating to your midterm, right? So either primarily, I think we will probably spend the time on looking over the sample midterms, but if you have some other questions, I'll answer that. So Greg?
For this problem, are we assuming that we must have all 10 different types of donuts per box?
No.
Then
because if you did, then the number of possibilities will definitely be much smaller.
Right.
So you can see that. So suppose whenever I put 2 ones next to each other, right?
Yeah.
That means I don't have one of the types of donuts. I have 0, right? Because
okay.
when I say, let's say I have so that's a possible string, right? And what it represents is I have 12 donuts of the first type and no donuts of other types. Okay, so that's a good question. I should have already pointed that out. So yeah, so the point is that one of the things is that whenever you try to say the problem of counting this is the same as the problem of counting something else, you need to really convince yourself that each of the valid configurations on this side, there is exactly one valid configuration on the other side, right? So each valid filling of the donut box should correspond to exactly one such string, right? So and then you need to convince that each of those strings corresponds to one valid way of filling the box. And then you can, reduce the problem of counting the donut boxes to counting these binary strings, and then you have the answer. Okay. So so we'll pick up this counting, next Tuesday. So right now, again, take a break, and I'm going to, pause something because I'm also going to take a break for 10 minutes, and then I'll be back, and we will discuss the exam. Okay, so the recitation today is you're going to just hear more of me. Okay, so let's take a break and come back. So, but if there are any questions on the homeworks, I'm certainly happy to help.
Can you go over number 5 on midterm 1?
Number 5 on midterm 1.
Problem 5.
I'm sorry?
Problem 5, not number 5.
Right. So so I discussed problem 5 on Piazza, didn't I?
Yes.
Okay. So do you have a question about what's there on? So if there's something there that you don't quite understand, if you ask me, then I can. But anyway, why don't we get to that problem? I am on that sample midterm, so we can get there in a few minutes. Any other questions?
Number 3 on midterm 1.
Yeah, so I'll get to that too. So if your questions are about the sample midterms, then I'll simply go through them one by one, and then you have and then raise your questions when we get there. That's easy enough, and I probably am not going to. Yeah, so we'll okay, so why don't we get started? So a question like this, where you're asked to find equivalent propositional formulas, what you want to do is you want to simplify them as much as possible so that you will more easily recognize when you have the same formula. So for instance, if you take this, so if you take this, then you can take the negation and push it inside, right? Apply the De Morgan's law. Then that becomes, not P, and then R becomes and then it becomes not Q, which you can simplify as P and Q, right? And same way, if you push the not inside, this will become not P, R, not Q, and that further simplifies to not P, R, Q, which we know is another way of saying P implies Q, right? So once you do these simplifications, the things that are similar will simply just stare you in the face, and then you can go from there. Okay, so any questions on this? Okay, so I will. So this is a straightforward problem. So I'm not going to. It just gives you, just asks you about the definition of what is symmetric and what is transitive and so on. So I don't think there is. It's just a matter of working through the details. There's nothing really unusual here, right? So I'm going to skip this and move on to the third problem. Again, if you have something specific, you can always ask.
Wait, actually for problem 1, like how would you simplify number 7?
Okay, so So you simply factorize, right? So you see P and Q and R, not R and Q and P, right? So you can state it as, you can take Q and P outside, right? Then you would have R, R, not R, right? So this simplifies to true. So it just becomes, you see that, right?
Okay, thank you.
Right. So again, it's just one of those,
Is it similar?
Sorry?
Is it similar for 8 when you get like P or not P, that you, since it means true, you can just get rid of it?
Right. So you can distribute in the case of 8. So that becomes P R, right? So you can distribute this, it becomes right. Remember that you can distribute that way, and then this will become true, and then you'll just be left with P and not Q, right? Which we know, or rather P or not Q, which we know is Q implies P, right? So once again, something, or I guess P or not Q is already there, right, in that form. So again, the goal is to try to get it into some kind of a unique form, right? So if you can simplify it to a unique form, unfortunately, there is, for many of these formulas, your unique form doesn't necessarily exist, but try to get there, because if it's unique, then you can look at the form of the formula and then say, hey, this is the same thing, right? So that's the idea. Okay, so problem 3. So you're asked to express ux px, right? So which says there exist at least 2 values for which p of x is true, right? So if you try to express it using the existential quantifier, then you need to explicitly assert that there are 2 values for which p is true. So you would say there exists an x, there exists an y, p of x and p of y. But the problem is that if you just stop here, there is nothing that stops x and y from being the same things, right? You haven't still said that x and y are different. So you need to add the additional condition, right? So now you have the requirement that there are at least 2 distinct values for which p is true. So for the second part, you just have to say, for all is, is the same as not there exists not, right? And then using this, then you can just transform this into something that uses only for all. Okay, that's a more mechanical part of the problem.
I think someone's talking, but we don't hear him.
Is anyone trying to ask a question? Yeah, maybe not.
Yeah, I think Michelle was trying to say something and
Oh,
her
okay.
mic's not working.
Michelle, did you have something to say? Oh, okay. Yeah, I can see that you're trying to say something, but nothing is coming through. You can, if you're having trouble on audio, you can type it on the on chat. I'll see it.
I think Michelle wanted to ask that for the second and in the first question, can you replace and with such that?
So such that is just English, right? So this and?
Yeah, the first or the second one.
Or this one?
The second one, I suppose.
Yeah, such that is just somehow, not being comfortable with logic and being more comfortable with English. But yeah, such that is just English for and. Okay, so let's go on to this. So you will see that there are problems relating to power sets that get repeated. The purpose of these problems is that they get you to understand some of the so the goal is to get a better understanding of sets and sets of sets and what exactly all of this means. But I'm not going to, I do want you to understand sets well, but I'm not going to ask you these types of power set problems. So I'm not going to, because it takes a little bit of time to work through them. So I don't want to work through them, and you are, of course, welcome to do them because they do help you understand the concepts better, but I don't have the time and I don't want to go through that. So this problem, there's a solution in the, that I posted on Piazza. So you should go and look at it. If you have a question about that solution that was posted, then you're welcome to ask that question here. I can definitely clarify.
Professor, I do have a question about your solution. You stated that the answer would be part of S cross S, the relation, but what if the codomain wasn't S, as in, it would map S to the natural numbers or some other thing that was not an S?
No, when you say all binary relations on a set S, right? That terminology means that R, any relation R is a subset of S cross S, or in other words, R is a relation from S to S. That's a term. When you say relations on something, that means that both the domain and codomain are that set.
All right, thank you.
So again, we already did a homework problem where I said, show that the set of all possible functions over a countable set is uncountable, right? And so this is saying all possible relations over a countable set, right? So that's going to be uncountable if you read this as, uncountably infinite. So when the problem says, example, when R is countable, it's countable if, S is basically a finite set, okay? But if it is a countably infinite set, then the set of all possible relations is going to be uncountable, okay? Because it's very easy to see, because a relation, as we said, is a subset of S cross S, right? And therefore, the set of all possible relations is really the power set of S cross S, right? Because every subset of S cross S is going to be one possible relation. Okay, so therefore we know that power set of S cross S is going to be uncountable if S is countably infinite, right? But if S is finite, then power set of S cross S is going to be still finite, okay, and therefore countable. So I can tell you that I don't, in the exam, there aren't any power set problems like problem 4. Otherwise, I would not say, I'm not going to answer the question. The fact that I didn't answer the question means that I'm telling you that it's okay not to know it. Okay, of course, it helps. Therefore, you should if you have time, certainly look through those problems, but I'm not going to ask them tomorrow or Thursday. So yeah, I think problem 6 also is, the solution is there, but it's really a trivial problem because the enumeration is already given to you, and therefore, by definition, it is, countable. But, because it's a sequence of infinite strings, and because we have done a proof that says that the set of all infinite strings is uncountable, right? So, so you may get confused that this is the set of all possible infinite strings, but that's not the case, right? This is a particular sequence of infinite strings that are being enumerated, for which you already have an enumeration, okay? And therefore, the set, by definition, is countably infinite. Any questions on that?
So to answer is the enumeration was already given, so it's already countable.
Right. That's why, there's, all these hints about Halloween and so on, right?
Okay.
Okay. And problem 7 is something that we didn't do. We haven't covered that material yet. So. So do you have any questions on the second midterm?
Just for question 1.
Yeah. It's the most confusing question that could be asked, right?
Yeah, so is A saying, like, can I interpret it as this is a proposition?
No, because if you did, no, it's not a full statement. It's just like a naming something, right? So while the problem is, the choices seem confusing, if you are clear about what you're looking for, which is a statement that can be either true or false, then the answer should jump at you, right? After, yes, there is a lot of confusing stuff over there, but there's only one statement that can be either true or false, right? Which ones do people think? Okay, other than A, which is a fragment, and therefore it's not quite clear. So
is it D?
Right. D is the only one that has, that could be true or false, right? So
But
if you
wouldn't
say
that
trust none of the above answers, well, it can't be true or false, right? Because again, the wording is a little bit confusing. If it said none of the above answers is true, then that would be a proposition, right? But it says trust, which is something that people can do, but it's not something that you can assign a true or false to it.
But wouldn't D kind of be a predicate as well? You know, it depends.
I'm sorry?
Very much. Wouldn't D also be a sort of a predicate since it depends on the context and very much on very conditional?
No, it's either true or false, right? In the end, that's all that matters. Is it true or false? How you can determine whether it is true or false is not a problem here, right? You're not being asked to decide, how will you know, is it true or false, right? In the same way, somebody asked something about C, and C is a question that has a yes or no answer, but that's not the same thing as true or false, right? The statement itself, you can't say is true or false. Okay, so
sorry, Professor, but
yeah.
I remember reading in the textbook there was like examples of stuff which are not propositions, but predicates was, the stock market will rise tomorrow, or it is 3 o'clock.
Yeah. So it is. So the stock market will rise tomorrow is something that you cannot tell whether it is. There is no way to say whether it is true or false right now, right? So you can't say that it's true or false, right? It is just a statement. Tomorrow, you can tell whether it is true or false. So it'll become a proposition tomorrow, but today it's not a proposition because there's no way, regardless of what, right? There's no way to say whether it's true or false. Okay. So anybody has a question on number 2?
Yeah, I was just confused on what the equation was showing.
This question?
Yeah.
Okay, so let's say, okay. So this is a Cartesian product of n sets, right? So S is a Cartesian product of n sets, and we know that S is, this Cartesian product is infinite set. Okay, so based on that, what can you say about S1 through Sn? So these are all, you've already been told that there is exactly one correct answer, right? So you don't have to worry about, there being multiple possible correct answers. So since there's only one, you pick the best one and move on, right?
On the exam, will we be told there's multiple answers?
Yeah, you will know whether the problem has a single answer or multiple answers, yes. In fact, I don't think it'll allow you to select multiple answers for single answer problems, right? I think that's how Blackboard is set up. So, right, so if you want to get an infinite set, then you must start with something infinite, right? So there's no way to get infinity from finite sets. So it must be the case that that is true. And then you can quickly go through the rest, and then you can say, those are not requirements. So for instance, there is no need for any set to be finite, and there is no requirement that, you can have a bunch of infinite sets, and if you take the cross product, you will still get an infinite set. Okay, so okay. Are there any questions on this? So you want this to be a bijection, right? Which means that and given the nature of this function, that its output is only integers, right? So you immediately know that anytime the second component, anytime the codomain contains fractions, you're not going to get bijections, right? Because none of the fractions are going to be pointed by f, right? F is only going to point to integers. So you can immediately rule out that and that and that, right? So now if you look at these two, you can see that on z to n, you're not going to have, none of the negative numbers in z can be mapped onto anything in n, right? Therefore, this is also going to be left out, and you're left with just z comma z. Okay, which is in fact an obvious choice, right? You don't even have to eliminate the rest. You can just say, hey, z works, and then you'll be right.
Could you explain why you can't have fractions again?
That's this function, right? The output is just integers, right?
Oh.
So therefore,
okay.
You want a bijection, which means that everything should be pointed to, right? So there must be an arrow coming into every element. Well, if there are no arrows coming into any fractions, then of course it can't be a bijection, so you can just throw them out. But again, you can also proceed from here and then say, yeah, that works. And then you can stop worrying about the rest. Okay, so this is a problem 4 and problem 5 don't apply. So, so go to problem 6. So if you talk about a reflexive relation over S, then it must always have A comma A, B comma B, C comma C, right? That must always be there. So you can immediately rule out that and that. And yeah, so those two can be ruled out. Oh no, this is still, yeah, that's ruled out. All right, so you only have these two as the possibilities. And now you just have to look at the definition, which basically says that the only pairs that can be there are the ones that are equal, right? Nothing else can be there. So essentially, reflexive says that everything that's equal should be there. And co-reflexive says that nothing that's not equal can be there, right? So clearly the only thing that's going to work is a relation that contains just pairs of the form A comma A, which is C, right? So that's how you get to the solution. So you can go through these.
Could you go?
Yeah. Go ahead, please.
Could you go over 5, or have we not learned that yet?
5 is not something we have covered. Right? 5 is number theory, and we haven't reached that part yet.
Now, does 7 also just have one answer? Because I was a little
Yeah.
confused by this one.
I believe that this is all, in the same question. Yeah, all of them have one answer, which of course makes your life easier. And yeah, it's for the same reason I don't like one answer questions. I like multiple answer questions. Because you have to know which ones are you can't just eliminate and then zoom in on the right answer.
Will you say how many answers there are to each question? Like if there's only 2 solutions to it or 3?
So you will, again, the question from the question type, it'll be obvious to you, right? It's going to present it to you in a way that, you have, n boxes to check, or, 1 box to check, or something like that, right? So the interface itself will make it, you can't do the wrong thing, right? Because it just won't allow you to do the wrong thing.
Now, for number 7,
yeah,
aren't C and D technically equivalent, because you can convert the implies into a not P or Q and have somewhat
Okay.
equivalent statements?
So let's get through that, okay? So so the first one, right? It doesn't say that there are exactly 2 elements, right? It certainly says that there are 2 elements, but there could be more than 2, and it doesn't really, say much about that, right? So it's not going to capture the condition that there are exactly 2, right? And B is simply false, right? Because you can't have it be the case always that every pair of elements be not equal, right? Because obviously it's false. So so coming to C, right? So C says, again, there are 2 elements, right? There exists X and Y. So it asserts the existence of 2 elements, right? And it says X not equal to Y, therefore the 2 elements are distinct, right? And then it says Z equal to X or Z equal to Y, right? So it says that basically no other elements exist, right? Because for all Z, that Z must be equal to either X or Y, right? So now you have said exactly 2 elements, right? Because there are 2 elements, X and Y, that are not equal to each other, and every other element must be one of X or Y, right? So we have a tight characterization of a domain with exactly 2 elements, right? So C is the answer. Now, looking at D, D also says that there are 2 elements, and the 2 elements are not equal, okay? And then what does it say? So for all Z in A,
Is it the ordering of the quantifiers which make the difference here, or?
that's what I'm trying to think. The last time I looked at it, I certainly thought it was clear, but now I'm getting confused. So Oh, I'm sorry. So I misread C. That's the problem. Okay. So so what C says is a little bit different, right? Because C has picked a Z in advance, right? So you can take a set like 1, 2, 3. Okay. Now you can set Z equal to 1. Okay. And now you need to pick X and Y in such a way that the rest of the formula will be true, right? So you're going to pick X equal to 1, Y equal to 2, right? If you do that, then C is going to be true, right? Because you first pick Z, right? Then you pick X and Y so that the rest of the formula is true. And you pick X equal to 1, Y equal to 2, you satisfy X not equal to Y, and you also satisfy Z equal to X or Z equal to Y. But obviously the domain has 3 elements, right? So the point is that you have to pick X and Y first and then say that any other Z, right, must be, any other Z you pick must be equal to X or Y. So the answer here is D, whereas C is something that because of the order of picking, you can make it work even if the set has more than 3 elements, more than 2 elements. Right?
Right. Thank you, Professor.
Yeah. So that's why it's a little bit tricky. Yeah. Okay. So once again, you have an uncountable set and then a relation on uncountable set, right? So we have seen this in the past. So this looks like it should be uncountable, right? The only wrinkle is that it says the relation is reflexive, okay? But reflexive just means that you're going to have every, pairs of this form are all going to be there, right? So the relation is going to be different because of whether it contains pairs of the form I comma j for I and j that are not equal, right? So 2 relations are going to be different because how they differ for I not equal to j, but they're always going to have I equal to j. So you can follow through these steps and you'll see that it's a valid proof. And so, you just have to say it's a valid proof. Okay. And the choices given here are if you think about the choices, you will see, it's not that difficult to rule them out. The conclusion is wrong, right? What that says is that the proof is right. So if the proof is wrong, then, it sort of doesn't make sense to talk about the conclusion being wrong, right? So the conclusion being wrong makes sense only if the proof is right. And you can go through the choices and you can easily eliminate all of them or you can just walk through the proof and convince yourself that the proof is correct. It's a standard proof that we have, standard form of diagonalization proof that we have done several times over. And so so you can go from there. So I think okay, so for problem A, you just have to understand that containment is like a subset, right? So if you think of R as a set of pairs, then containment means that one set is a subset of the other. And then once you know that it's a subset, you can say, of course, it's reflexive, it's not symmetric, and it's transitive, right? So, so that's all you need to do. And this is another power set problem, but we can certainly work through that. So if A is this, then you will certainly have a subset that contains just that element. So that definitely belongs to P of A, but here you have 3 braces, right? Set of set of set, and that's not in the power set, right? Because basically you take an element here and you can put one more brace around it and that'll belong to the power set, right? So that's why you have 2 braces, but not 3. So this is completely meaningless, right? Because the way you do a Cartesian product is you take one element from A and pair it with, one element from this one, right? So so the pairs should be of the form things like this, right? It doesn't even have this form, right? Because the Cartesian product must have, parentheses and something inside the parentheses. So it's just completely off, right? So, and this is of course correct. So if you take the empty set, product with anything, then of course you just get the empty set. So the question asks you, okay, so there is A is an infinite set, B is a countable set. Again, whenever you hear a countable, you always think, okay, it can either be finite or uncountably, I'm sorry, either it's finite or countably infinite, right? So you need to consider those 2 cases separately in most cases, right? For most problems, you need to think about the 2 cases separately. And now it asks you which, when do you have a bijection? And the way to read that is when are their cardinalities the same, right? When do they have the same cardinality? That's the question when you say, is there a bijection? Okay. So A is infinite, B is a countable set. Okay. And I think these are problems for which one or more answers are correct. Okay.
Oh, when they say infinite, do they mean infinitely countable? I mean, infinitely uncountable?
No, infinite means anything infinite, right? So it can be, we talked about an infinite series of infinities, right? In the class. So it can be any of that, right? All you are told is that it's infinite.
All right.
So, and it also asks you what must be true, right? It doesn't say what can be true, what must be true. What are the two sets that must have the same cardinality? Given that A is infinite and B is countable, you can't say that the two must have the same cardinality, right? So obviously A is false. Then if you look at A and P of B, again, you cannot say anything because B being a countable set could even be finite, and therefore P of B may be just finite, right? So you cannot say B must be true. So what about A and A intersection B? What can you say about that? Greg?
Intersection B could be finite, so you'd have infinite and finite again, which doesn't work.
Right. So again, it's an application of some of the things that we have seen. So if you have two infinite sets and you take the intersection, that may end up being finite, right? And therefore we cannot, and then obviously there's not going to be a bijection between finite and infinite. So C cannot be true. What about D? A and A union B.
But I think that works, right?
Yeah, because like the union of infinite and like finite would be infinite.
Right. So what we know from this statement is the cardinality of A is greater than or equal to the cardinality of B, right? Because a countable set is the smallest infinite set, right? So if A is infinite, it must be countable or uncountably infinite, right? So therefore A has a larger cardinality than B. Therefore A union B, right, should have the, because A has a larger cardinality than B, adding the elements of B to A shouldn't really increase the number of elements in A. Okay, so that's the way to think about it, right? Just like adding a finite number of elements to a countably infinite set doesn't increase its size, or adding countably infinite number of elements to a countably infinite set again doesn't increase the cardinality. Therefore, we can say that whenever this holds, then among infinite sets, then you add this. That doesn't make a difference. Okay, so and you can verify that. What about A and A cross B? Anybody other than Greg wants to try? Okay, Greg, go ahead.
I think they should also have the same cardinality by the reasoning of when you have countable cross countable, it's still countable.
Right.
So we can kind of extend that to say uncountable cross uncountable is probably going to be uncountable.
Right. So this kind of reasoning that if you have infinite sets and A's cardinality is greater than or equal to that of B, then A cross B will still have the same cardinality as A. Okay, so that still works for both D and E. Okay. So which of the following statements is true? I think this is this is sort of a more straightforward problem, right? So because we know that n cross q is countable, we also know that power set of q is not countable. We know that if you we have done a problem in class, I think, of taking the union of countably many countable sets, right? You can when you have a countably many countable sets, you can just write them down in a sequence, and then you can just do the same thing as we do with rational numbers. Pick one element from the first set, then two elements from the first set, and the one element from the second set, and so on, right? So there's a way of enumerating all the elements of the union. So so D is countable, and so on. So I think this is a sort of a straightforward problem.
Could you go over E? Because I wasn't sure if that was true or not.
Your audio was some lot of sound, so I couldn't hear you.
Sorry. Could you go over E? Because I wasn't sure if that was true or not.
Can I go over which problem? I'm sorry.
No, just I wasn't sure if E for this problem was true or not.
Okay, so I'll just repeat. So Greg, did you have a question, or you forgot to? Okay. So we know that n cross q is countable, right? And we know that the set of all binary relations on a countably infinite set, right? We already done this, right? So this is not countable, right? If you consider the binary relations, all binary relations, then you're dealing with something like a power set problem, and therefore it's not countable. Power set of q, almost by definition, is not countable. And union of countably many countable sets, right? That's going to be countable, which we just went over that. And E, the intersection of finitely many uncountable sets, can be countably infinite. And what we have said about intersection is that you can start from anywhere and you can end up with even finite sets or even empty sets, right? So therefore, when you apply intersection, the result can be anything. All you can say is that the result of intersection cannot, increase the size of the set, right? But it can decrease it arbitrarily. And therefore, if you have finitely many uncountable sets and you take the intersection, you can end up with even the empty set. So, or countably infinite set, anything is possible, right? Anything else? Any other questions? I think there's a power set problem that I'm going to, again, not go through. And the next is a counting problem that I'm not going to go through. Okay. So we are pretty much, all the applicable problems we are done on this one. Okay, I'm going to skip the power set problem and then so you're given this function, right? F of x equals x square, right? And you're asked to identify a domain on which this function is injective but not surjective, right? So that means you have to choose a codomain where some elements are left out, okay? And in addition, there shouldn't be two elements in the domain that map to the same element in the codomain, right? So because you want it to be injective, right? And when you see x square, you see that, okay, the nature of x square is that both the negative x and positive x are going to map to the same point, right? So if you want this to be injective, then you need to leave out all the negative numbers in the domain, right? Because the moment you have a negative number in the domain, then you could the result may not be injective, okay? And then you want to leave, you want to have non, squares on the codomain, right? Non-perfect squares on the codomain, so that there are some elements that are left out, so that this won't be surjective. So if you take, if you take the domain to be the set of natural numbers and the range to be set of natural numbers, that's going to work, right? Because on positive numbers, x square is uniquely defined, and there is only one x that will produce a particular value of x square, right? And then there are numbers like 3 and 5 in the codomain that for which there won't be any arrow coming into it, right? So therefore, it is not surjective. Do you have any question?
Would x being positive real numbers and y being all real numbers work also?
So somebody was saying something, but the volume was so low that I cannot hear.
I'll just type it.
You can type it in if you want. Yeah, that'll work. So the question was whether x being positive real numbers and y being all real numbers, will that work? That'll work. Because there are no negative numbers in the domain, therefore it can be the x square function is going to be injective. And since the codomain has negative numbers and there's nothing that's going to come into negative numbers, so it's not going to be surjective, right? So the answer is, that answer will work. So surjective but not injective, right? So then you immediately know that, something like natural numbers won't work because, there are going to be numbers like 3 and 5, no arrow is going to come into it if the function is x square, right? So you know that the codomain in this case has to be like a real number, right? So I'm sorry. So you know that the domain is going to be real numbers, because otherwise you cannot be surjective, right? Because otherwise you will not be able to reach numbers like 3 and 5, right, by squaring. So the domain has to be something like a real number, and then since there is no need for the function to be injective, right, then it doesn't matter if the domain contains negative numbers, right? But the range shouldn't contain negative numbers, because then it can't be surjective, right? So if you take X being the set of so if you take X being the set of real numbers and Y being the set of positive real numbers, then this is going to be surjective but not injective, because 2 points will map to the same point. Okay. Any questions on this? So for it to be bijective, then what can we say? So we already have the case for surjective, right? So a simple tweak on that is to make the domain to be positive real numbers. Then if you go from positive real numbers to positive real numbers, then you can have this be a bijection, right? Because every positive number has a positive square root, and every positive real number has a square, right? So that way it becomes a bijection, right? So because you have, this is the x square function, this is square root function, right? So it's going to be, both of which are, functions, right? We know that square root is a function when you take just the positive square root, and therefore, because both are functions, you're going to have a bijection here. So if you use a finite set, often, the problem is that there's nothing that prevents you from using finite sets, but for a problem like this, finite sets, yeah, I guess it can work in some cases. Yeah, I don't know for what cases it will work. Of course, the problem allows you to choose X and Y in whatever way you want, right? There's nothing about the problem that says you can't do it. So so this problem is pretty straightforward, right? So I think, other than the fact that it has quotes from Shakespeare and other works of literature, there is nothing in this particular question, right? So obviously the set of all words is finite, right? Because there's a finite alphabet, and words presumably have a finite length. And once you say the words are finite length and you start from a finite alphabet, then the number of possible words is finite, and therefore obviously countable, right? And if you talk about real numbers, well, real numbers are the set of real numbers is uncountable. So I believe that the question paper has something about well, okay. All I can tell you is that when I give you an exam, I will make it clear whether I expect an explanation or not. Okay, so my feeling is that from the way this problem is structured, the instructor is expecting an explanation. That's why you have the space, right? You have been given the space. Otherwise, there will be a fill in the blank yes or no type thing. So you're supposed to give some explanation, but the explanation need not be very long, right? It's definitely not asking for a proof, right? It's asking for some evidence that you understand why the answer is such and such.
If we need to like show work, like would we like type up the work in the text box, or do we have to like upload a picture of our scrap paper?
No. You cannot upload anything because as I said, it's going to be difficult. So you're going to type it in. I'm going to give you only questions for which the answer does not require you to draw a picture.
Okay. Thank you.
Yeah. So problem 4, again, it's about the order of quantification, right? So if you pick an m first, and then you want to find an n such that m plus n equal to 4, that's can be easily done when you're dealing with integers. But if you want to pick an m that's going to result in a sum of 4 when added to any number, right? That's the case too. Well, that's not possible. So, it's a, I guess we had a homework problem like this, right? So. Yes, another power set problem that I don't want to. So this is an induction proof problem. And so once again, we haven't covered induction yet. So this is not something that you need to worry about. And this is a problem that we have already asked, and I missed the solution in the, in the posting. I will update the solution and post it, and then you can see it. So I think that sort of means we are done, right? All the 3 midterms we have gone over. So if you still have any questions, you can ask. Otherwise, we can conclude and you can go back to study.
Professor, can I ask a question about the well ordering principle? I don't remember if we did that in class, but I do remember reading about it.
Well ordering is something that we did not cover in the class. So we will get to that when we talk about induction, we will talk about that, okay? So well ordering is one of those things which seems kind of obvious, and there are places where we have made that, we have made that assumption without specifying it, but we will just leave it at that, not worry about it now until we get to induction.
All right, thank you.
Does the same idea of leaving a question blank and getting 25% of the credit apply for our test as well?
If it is true, I will let you know.
Okay.
Because again, that makes sense only for certain types of questions, right? So if there is an multiple choice question and you leave it blank, then you're not going to get 25%, right? Because I actually want you to try to solve the problem, right? And not just say, I'm not even going to try. So but so that really works well for things like proofs, where if you don't have any idea and you write something, then it becomes extremely hard for us to grade. So that's where this type of incentive is helpful for you and us. But for other types of problems, and sometimes about where you have to provide a justification. Again, if you don't have any idea, it's better for you to, it's better for both of us if you leave it blank. But otherwise, I do want you to make an attempt. And because I think basically if you make an attempt, if you make a mistake or get it right, either way, you're going to remember better, right? If you just leave it blank, I don't think you're going to remember what you did. And so I don't want to encourage that unless, except for proofs. Any other questions?
Oh, would there be around like 7 problems with like each of them having like smaller sub-problems to them?
I'm not saying how many problems are there because it's not that meaningful, right? Because I can give you one problem with, 20 parts or 20 problems with one part. So it's a little difficult to say. What I can tell you is that because I'm structuring it as 2 midterms, the first midterm is not going to be as tricky as the midterms that you have seen here, right? It's going to be a little bit more straightforward. In terms of length, I think the examples you have seen are variable in length. I think some of them are not that long and some of them are somewhat long. And the one that I'm giving you, again, I really don't know. I think it's something that you can finish, but again, focus on doing some problems well, as opposed to trying to get a little bit of everything right. Okay, so that's what I would recommend to you, because you have to think about the problem, and once you have started thinking about the problem, you might as well try to get it done well. Okay. Anything else? Okay, otherwise, good luck with your exam. And yeah, keep watching on the on Piazza because we may post, some more clarifications about the exam or update the solutions and so on. I think there was one mistake that was pointed out in the homework 3 solution. The relation to the power 3, right? So cube relation was missing one pair, right? So if you looked at it carefully enough, then you would have seen that that's missing. So when I add the solution to the transitivity problem, I'll fix that. So you will see updated posting sometime tonight or maybe tomorrow morning. Okay. So otherwise, good luck. I will continue to stay here for a couple of more minutes to see if there are any more questions, but otherwise feel free to drop off and do the other things that you need to do. Thank you.
Professor, can I ask a question about cardinality?
Yeah, sure. Yeah, go on.
For the question with the A union B, I originally thought that it would be A and A union B would not have the same cardinality because A union B would always be strictly larger than A.
So if you look at your textbook, and also I believe it was there in the slides, the definition of an infinite set is that there is a bijection between that set and the set union something finite.
So then it's more like, so then is it just more generalized in the fact that since they're both countably infinite, we give them the same value as countably infinite and say they have the same cardinality?
Right. So remember that the way we count cardinality for infinite sets is by establishing a bijection, right? So essentially we pair up the elements and say that if every element has a pair and everybody has been paired up, then the two sets must have the same number of elements, right? And this way of counting is a little bit, has a somewhat unintuitive behavior in the sense that it's able to add some elements and to the original set and still be able to maintain this kind of mapping. Okay, so this is why we are able to say things like n cross n and has the same cardinality as n, or z has the same cardinality as n, right? I mean, you could think of z as n union n with after applying a negative sign to every number in the second n, right?
Yes.
So that's, we know that those two have the same cardinality. So so essentially, right? So basically, you can remember what I wrote. If A and B are infinite and the cardinality of A is greater than or equal to the cardinality of B, then the cardinality of A union B will be equal to the cardinality of A, right? This is something that you can, this will always work, right? So among infinite sets, adding elements that are, at the same level of infinity or a lower level of infinity does not change the number of elements in the set, right? So this means that if this is some infinity, right, this is a bigger infinity, right? So and what it says is that a set that corresponds to a bigger infinity, if you add the smaller infinity to it, it doesn't make any change to the number of elements. Okay, that's the nature of infinity.
Okay, thank you. Because originally I was thinking that A would be greater than A because we're adding some elements to, or A union B would be greater than A because we're adding elements. But now I see that it's just about bigger infinity, infinity being the same.
Right, right. So in fact, the definition of an infinite set is, A union, right? There exists a bijection from, right? So that's the definition of an infinite set. Okay, so you can add an element, and if you can establish a bijection from A union B to A, then you can conclude that A is infinite, right? Or if A is infinite, then you can conclude that this bijection exists. Any other questions? Okay, very good. So good luck with your exam, and I'll see you next week.